Have you ever really thought about how the crazy heat inside a power plant furnace actually turns into the electricity that charges your phone? Well, it's not magic, not at all. It's this incredible field of engineering called Applied Thermodynamics, and today we're going to break down exactly how it all works. So yeah, that's the big question, right? How do we actually do it? How do we take the raw energy from burning fuel or even from a nuclear reaction and somehow convert it into useful work and the electricity that powers our entire world? That is exactly what we're going to get into today. And here's our game plan. First up, we're going to start with the absolute basics, the core idea of turning heat into work. Then we'll look at the perfect engine, the theoretical dream. After that, we'll see how engineers take that dream and turn it into a real-world workhorse. We'll even take a quick tour inside a power plant to see it in action. And finally, we'll check out the super clever ways they squeeze every last bit of efficiency out of these systems. All right, let's just dive right in. To really get a handle on how we generate power, we first have to talk about the field of study that makes the whole thing possible. So, this isn't just theory from some dusty textbook. This is the hands-on science of building the engines that make everything go. And the key concept here is something called a thermodynamic cycle. Just think of it like a recipe. You take a substance, let's say water, and you put it through a loop. You heat it up, you let it expand, you cool it down, and you compress it over and over again. This constant cycle forces that substance to do useful work for us, like spinning a giant turbine. Now, before we jump into the engines that are actually out there in the world, we need a benchmark. We need a theoretical gold standard that tells us the absolute tippy-top maximum efficiency we could ever hope to get. And that, my friends, is the ideal engine. The Carnot theorem basically sets the ultimate speed limit for efficiency. What it's saying is that a perfect engine, one that runs so flawlessly that every single step could be run backwards without losing any energy to stuff like friction, well, that engine will always be better than any real-world engine. It's the theoretical peak performance that engineers are always chasing. So this ideal Carnot cycle is this perfect four-step dance. First, you add heat, but you do it while keeping the temperature perfectly constant. That's what isothermal means. Next, the fluid expands and does work, but with absolutely no heat escaping. That's an adiabatic process. Then you pull heat out of it, again at a constant low temperature. And finally, you squeeze it back to where it started, again with no heat transfer. It's literally the perfect blueprint for turning heat into work. Okay, so if the Carnot cycle is the perfect blueprint, how in the world do you adapt that for reality? Well, this is where some seriously clever engineering comes in, to bridge that gap between a perfect theory and something that actually works. And that is a fantastic question. I mean, if Carnot is the best, why not just build it? Well, the problem is, trying to actually achieve those perfectly reversible processes is next to impossible. For example, that last compression step in a Carnot cycle using steam, you'd be trying to compress this wet, slushy mixture of liquid and vapor. A pump would just get destroyed by the water droplets hammering it. It is an absolute engineering nightmare. And this right here just lays it all out, doesn't it? We have to trade a little bit of that perfect theoretical efficiency of the Carnot cycle for the rugged reliability and practicality of the Rankine cycle. The Rankine cycle is the real workhorse that actually keeps our lights on. So let's take a quick look under the hood of a typical steam power plant and see the four key pieces of equipment that bring this Rankine cycle to life. It's this incredibly powerful, continuous loop. Okay, so first, the pump takes liquid water and puts it under immense pressure. That water then gets sent into the boiler, where it's blasted with heat and turned into high-pressure, superheated steam. Now, this steam is the powerhouse. It expands like crazy through a turbine, spinning it at incredible speeds to generate electricity. Then, after it leaves the turbine, the now low-pressure steam goes into a condenser, gets cooled back down into liquid water, and is ready to get pumped and start the whole journey over again. But, a basic cycle is really just the starting point. The real game for engineers is innovation. They're constantly trying to figure out ways to squeeze every last bit of useful energy out of this fundamental process. The name of the game is all about increasing thermal efficiency. It's a simple number that tells you, for every unit of heat you put into that boiler, how much useful work do you actually get out? A higher number is always better. It means less fuel burned, lower costs, and fewer emissions for the exact same amount of power. So the number one rule for improving efficiency is actually pretty simple. Get the steam hotter. The hotter you can make that steam before it hits the turbine, the better. See, higher temperature steam just packs more of an energy punch, which means it can do more work as it expands. This is exactly why power plants use superheaters, to get that steam way, way above its boiling point. It's all about getting more bang for your buck from the fuel you're burning. Now, one of the most clever tricks they use to boost power is called reheating. It's really cool. Instead of letting the steam expand all at once, they do it in stages. After the steam does some work in a high-pressure turbine, they actually send it back to the boiler to get another blast of heat. Then, this reheated steam goes into a low-pressure turbine to do even more work. It's basically like giving the whole cycle a turbo boost, and it massively increases the total power you get out. Okay, so while the Rankine cycle is the undisputed king of big power plants, it's definitely not the only cycle out there. Different jobs require different kinds of engines, and those are all modeled by their own unique thermodynamic cycles. Take the gasoline engine in your car. That's modeled by the Otto Cycle, where a spark ignites the fuel and air, causing a super fast combustion at constant volume. A big rig, on the other hand, probably uses a diesel cycle. It compresses air so much that it gets hot enough to ignite fuel all by itself, and that happens at constant pressure. And the jet engines on an airplane? They use the Brayton cycle, with continuous combustion to create that powerful thrust. Each one is a totally unique thermodynamic solution, engineered perfectly for its specific job. So, from the theoretical perfection of Carnot to the real-world power of the Rankine cycle, the whole story of thermodynamics is one of relentless improvement. And as we push harder and harder for cleaner energy and better efficiency, the real question isn't just if we can do better, but what will the next generation of power cycles even look like? Will they use new fluids, crazy new materials, or maybe entirely new principles we haven't even thought of to power our world? The engineering journey? Well, it is far from over.